Welcome back, everyone. In today's lecture, we're going to continue our discussion on wind loads, this time focusing on the National Structural Code of the Philippines. Specifically, we'll be looking at Code C101-2015 edition, Section 207 B.2-1. The example we will be working on is example number 2. It's actually the same building problem we solved in example 1. But here's the difference. Instead of applying the components and cladding method, we'll be using the main wind force resisting system approach, or simply MWFRS. This approach shifts our perspective. Instead of analyzing individual building parts like walls or windows, we'll focus on how the entire structure responds to wind forces as one system. All right, let's get started with the calculations. First, let's define the building dimensions. Capital B represents the horizontal dimension measured perpendicular to the wind direction in meters. Meanwhile, capital L represents the horizontal dimension measured parallel to the wind direction, also in meters. In example number 1, we already established that the roof dimensions are 7.2 meters by 15 meters. Now, if we take into account the lower portion of the building, we need to adjust for the roof overhang. This means the actual building width is 7.2 meters minus the overhang. So, considering the wind direction, B becomes 5.2 meters, while L remains 15 meters for the lower portion of the structure. Alright, now let's turn to the code and review the provisions in section B.2-1, since this will guide the steps of our calculation. The code tells us that for enclosed, partially enclosed, and open buildings of all heights, the wind load calculation is carried out in a sequence of calculations. We begin by determining the risk category of the building or structure, which is found in Table 103-1. Next, we identify the basic wind speed capital V for that risk category. This comes from Figure 207A.5-1A, B, or C. After that, we gather several important wind load parameters. These include the wind directionality factor, K sub D, the exposure category, the topographic factor K sub ZT, the gust effect factor G, the enclosure classification, and the internal pressure coefficient, represented by GCPI. Each of these values is taken from the appropriate sections and tables of the code. We then determine the velocity pressure exposure coefficient, K sub Z or K sub H, using Table 207B.3-1. Once that is in place, we calculate the velocity pressure, Q sub Z or Q sub H, using equation 207B.3.1. We also need the external pressure coefficient, C sub P or C sub N. And finally, with all of these values defined, we can calculate the wind pressure, P, acting on each surface of the building. When we look at Table 103-1, the code gives us 5 possible occupancy categories. The choice depends on how critical the building is and what purpose it serves. We use the occupancy category together with the exposure category when referring to the wind speed map shown in Figure 207A.5-1. In this lecture, we will also cover other important parameters, including the wind directionality factor, the gust effect factor, the enclosure classification, and the internal pressure coefficient. We'll also be discussing the height and exposure coefficients, K sub Z and K sub H, which describe how wind pressure changes depending on the height of the structure and the surrounding terrain. These coefficients will then be applied to calculate the initial pressure values, Q sub Z and Q sub H, which form the basis for determining the wind loads on the structure. After finding the initial pressure, we adjust it by applying the wall coefficients C sub P or C sub N, which account for how wind actually acts on different surfaces of the building. Finally, we include the effect of internal pressure. This adjustment combines with the external pressures and leads us to the final values that will be used in design. Let us now solve the problem. In example number 1, We already determined the occupancy category. If you have not watched that video yet, the link is in the description below. For this building, the occupancy is category 4, which corresponds to residential use. The wind speed is also something we already know. It is 260 kilometers per hour. Now, under section B.2-1, the code requires that wind speed be expressed in meters per second. So, if we divide 260 by 3.6, we get 72.22 meters per second. Strictly speaking, before we deal with wind speed, we need to establish the exposure category. As we saw in example number 1, this building is located in a built-up urban environment, so the exposure category is B. Now, there is a new factor we need to consider. To use section B.2-1, we must include the directionality factor, K sub D. This factor accounts for the reduced probability that the maximum wind pressure will act on all building surfaces at the same time. In other words, it recognizes that wind usually strikes one direction more critically than the others. For this building, which we are treating as part of the main wind force resisting system, the value of K sub D is 0.85. Just like in example number 1, we also need to check for the topographic effect. The topographic factor, K sub AT, accounts for the way wind can accelerate when it flows over hills, ridges, or escarpments. If a building sits in those conditions, the wind pressure can increase significantly. For our case, the value of K sub AT is simply 1.0. That is because the site does not fully meet the criteria in the code for applying a topographic adjustment. Since at least one of the 5 conditions is not satisfied, no adjustment is required, so the factor remains equal to 1. Another new factor we need to include is G, also known as the Gust effect factor. This factor adjusts the wind pressure to account for turbulence and the fluctuating nature of wind. In simple terms, wind does not blow at a constant steady rate. It comes in gusts. The gust effect factor corrects for this by amplifying the mean wind pressure so it better represents what the structure actually experiences. In NSCP C101-15 section 26.9.1, the gust effect factor for a rigid building or other structure is permitted to be taken as 0.85. Meanwhile, section 26.2 of the same code defines what is considered flexible. A flexible building or structure is described as a slender system that has a fundamental natural frequency less than 1 Hz. In other words, if the structure vibrates more slowly than once per second, it is treated as flexible. So if the natural frequency n is greater than or equal to 1 Hz, the structure is considered rigid. In that case, the gust effect factor capital G is taken as 0.85. There are a few recommendations on how to determine the natural frequency of a structure. According to NSCP section 2078.9-2 and section 2078.9-4, the natural frequency can be estimated using simplified formulas. For structural steel moment resisting frame buildings, the expression is N sub A equals 22.2 divided by H raised to 0.8. For other types of structures, the formula is N sub A equals 75 divided by H. If we apply the first formula using the mean roof height of 10.35 meters, the natural frequency comes out to about 3.42 Hz. Since this value is greater than 1 Hz, the structure is classified as rigid. That means we can take the gust effect factor capital G as 0.85. However, it's important to point out that there is a typographical error in the drafting of the NSCP. This means that some parts of the texts may not fully align with the intended provisions, and we need to interpret them carefully in light of the source references, such as ASC 7. As clarified in ASCE 7, the variable h in the formula is actually intended to be in feet, not in meters. This is the source of the typographical error carried into the NSCP draft. We convert the mean roof height of 10.35 meters, which is 33.96 feet. By converting the height into feet, which is the proper unit in the formula, the computed natural frequency becomes about 1.32 Hz. This value is still greater than 1 Hz, confirming that the structure is rigid and that the gust effect factor remains at 0.85. Instead of converting the height into feet, another option is to simply revise the equation itself, rewriting it so that the height is expressed directly in meters. So the first equation, n sub a, which is 22 over h raised to 0.8, can be rewritten in terms of meters. After adjustment, it becomes 8.582 divided by h raised to 0.8. The second equation, 75 over h, can also be adjusted. When expressed in meters, it becomes 22.86 over h, where h is now taken in meters. If we apply the revised equation for steel structures, using the height in meters, we still arrive at the same result of about 1.32 Hz. This confirms that the adjustment we made to the formula is valid. In other words, whether we convert the height into feet and use the original ASCE equation, or we use the modified version that works directly with meters, the outcome is consistent. The natural frequency remains greater than 1 Hz, which means the structure is classified as rigid and the gust effect factor stays at 0.85. Other than simply taking G as 0.85 for rigid structures, the code also provides a more detailed procedure for evaluating the gust effect factor. This step-by-step method is outlined in sections 207A.9-6 through 207A.9-9. It allows us to calculate G more precisely. For flexible structures, the code provides a separate set of provisions, which can be found in sections 207A.9, 10 through 207A.9, 16. We won't go into those details in this lecture, because the analysis is more complex and deals with the dynamic response of the structure to wind. That topic is better handled in a separate session. Now that we have the gust effect factor, let us solve for the internal pressure coefficient GCPI. Based on the table from the code for a fully enclosed structure, this factor is plus or minus 0.18. This value accounts for the potential pressure buildup or reduction inside the building due to openings like doors or windows being subjected to the wind. Next, we will solve for the velocity pressure exposure coefficients K sub z and K sub h. These values are obtained from the provisions of section 207B.3-1. Instead of relying only on a table, the code actually provides a formula. For a height z between 4.5 meters and the gradient height z sub g, K sub z equals 2.01 multiplied by the quantity z over z sub g raised to the power of 2 over alpha. If z is less than 4.5 meters, then we do not use the actual height. Instead, we substitute 4.5 meters into the same formula. This prevents the coefficient from becoming unrealistically small for very low heights. To simplify, we can unify the rule into a single expression where K sub z equals 2.01 multiplied by the quantity z over z sub g raised to 2 over alpha, where z is always taken as at least 4.5 meters. The values of z sub g and alpha are not arbitrary. We obtain them from table 207A.9-1 of the code. Now let us go back and define what z is. Z is the height of the level being investigated. In other words, it is the vertical distance above the ground at which the wind pressure is evaluated. This means that as z increases, the exposure coefficient also changes, reflecting the fact that wind speed generally grows stronger with height. This also means that z may vary from 4.5 meters up to the mean roof height, since all levels from 0 to 4.5 meters are treated as the same. Now that we have established the velocity pressure, the next step is to solve for the external pressure coefficient C sub p. We begin with C sub p provisions. It is defined as the ratio of the local wind pressure acting on a surface to the surface dynamic pressure. For walls, the values of C sub p are straightforward. The windward wall, in particular, usually carries the highest positive pressure since it faces the incoming wind. The other wall types are just the same. For roofs, however, the situation is more complex. The coefficient values depend on factors such as roof slope, wind direction, and the specific roof zone being considered. For the external pressure coefficient on walls, the code provides distinct values depending on which wall surface is being considered. The windward wall is assigned a positive coefficient because it takes the direct impact of the wind. On the other hand, the leeward wall carries a negative coefficient, and its exact value depends on the ratio of the building length to its width, L over B. The sidewalls also experience negative pressure, though their coefficients are generally consistent and do not vary with building proportions in the same way as the leeward wall. For the external pressure coefficient on roofs, the code presents a more detailed table. Unlike the walls, the roof coefficients vary depending on roof slope, the specific roof zone, and the direction of the wind. Some roof areas may experience suction, while others may carry positive pressure. This makes roof analysis more involved compared to the simpler case of walls. We will now proceed to solve for the wall external pressure coefficient C sub P. To begin, let us consider the building with the wind direction applied. Next, we define the key variables. Capital B is the width of the building measured perpendicular to the wind. Capital L is the length of the building measured parallel to the wind. Small h, or the mean roof height, is the average height of the roof above ground level, and theta represents the roof angle. For this building, the values are as follows: B equals 5.2 meters, L equals 15 meters, H equals 10.35 meters, and the roof angle theta is 36.87 degrees. For the windward wall, the external pressure coefficient, C sub P, is taken directly as 0.8. For the leeward wall, we first compute the ratio of L over B substituting the values. L equals 15 meters and B equals 5.2 meters. The ratio is 0.47. Since this value is less than 1, we use the corresponding coefficient for leeward walls from the code table. For the leeward wall, C sub P is negative 0.5. For the sidewall, C sub P is negative 0.7. We will now solve for the roof C sub P. Note that for the roof the planned dimension L is 7.2 meters, not 5.2 meters as used for the walls. Using H equals 10.35 meters and roof L equals 7.2 meters, the ratio H over L is 10.35 divided by 7.2, which equals 1.4375. For the roof, the key parameter is the ratio H over L, which we just computed as 1.4375. Use this H over L value to locate the appropriate row in the roof C sub P table. The table is organized by H over L ranges and by roof slope. We will use only the rows for H over L greater than 1, since that is the applicable range for our roof. If H over L were not greater than 1, we would select the other row and perform interpolation as needed. Next, isolate the columns for roof slope between 35 and 45 degrees. Because our roof angle is 36.87 degrees, it falls between those two columns. We insert 36.87 as the target slope. Finally, we will interpolate between the tabulated values for 35 and 45 degrees to obtain the precise C sub P for each roof upper and lower limits. Use linear interpolation in the slope direction, and if required, the value of C sub P for the lower limit after interpolation is negative 0.1626. For the corresponding roof zone, the interpolated C sub P at the upper limit is 0.2187. For the leeward wall, the value of C sub P is negative 0.6 since the roof angle is greater than 20 degrees. We now solve for the velocity pressure Q sub Z. So here is the front view of the structure for reference. The basic expression we use is Q sub Z equals 0.613 times directionality coefficient topographic effect factor and velocity pressure coefficient times V squared. The term Q sub Z is derived from the dynamic pressure Q, which itself comes from the conservation of fluid momentum. The simplified differential form for steady In viscid flow along a streamline is dq over dx equals rho v times dv over dx. Integrating that relation along a streamline leads to Bernoulli's form, which gives the pressure-velocity relationship, leading to the dynamic pressure, Q as 1/2 rho v squared. Using the standard air density rho equals 1.225 kilograms per cubic meter, the factor 1/2 rho becomes 0.6125. That is why the constant in the code is reported as approximately 0.613. In practice, we do not stop at the dynamic pressure. We multiply this base value by the exposure and site modifiers K sub z, K sub zt, and K sub d to obtain the design velocity pressure Q sub z used in the wind load equations. Do not forget, though, that Q is in Pascal and the value of V must be in meters per second. After solving the initial pressure Q sub z, we will then solve for the final pressure P by accounting for internal pressure effects, so the equation will become Q times G times C sub P minus Q sub I times GCPI. To account for the duality of internal pressure, we will replace the minus operator into plus or minus. The code has a provision specification for Q sub I. It is taken as Q sub h for windward walls, side walls, leeward walls, and roofs of enclosed buildings, and also for negative internal pressure evaluation in partially enclosed buildings. Q sub z is used for positive internal pressure evaluation in partially enclosed buildings, where the height z is defined as the level of the highest opening in the building that could affect the internal pressure. For positive internal pressure evaluation, Q sub I may conservatively be evaluated at the mean roof height. This is why, in practice, Q sub I is often simplified as Q sub h. Let us now organize the values into a table, with the first column showing the height z. For the windward wall, z will vary, while for the other wall types, the values remain uniform. For the windward case, the selected heights correspond to the critical levels of the structure, the floor levels at 3, 6, and 9 meters, and finally the mean roof height at 10.35 meters. Although we did not include z at 0 meter elevation, since it is just the same as 4.5 meter elevation, it could also help to emphasize that from 0 to 4.5 meters, the pressure is constant. This can be done by adding the 0 elevation as part of the table. Next, we account for the code provision that z cannot be taken as less than 4.5 meters. For any level with a height below this threshold, we replace the value of z with 4.5. These adjusted values are then listed in a separate column of the table. The next column in our table will contain the values of K sub z. The formula is 2.01 multiplied by the quantity z1 over 365.76 raised to the power of 2 over 7. Here, z sub g and alpha have already been replaced with the appropriate values. We now plug this formula into the calculator, replacing z1 with the variable a. This way, we can use calc function to substitute the different values of z from our table. After entering the formula, we press the calc button. The calculator will then prompt us for the value of a. At this point, we simply provide the value of z, one at a time, starting with 4.5 meters. Finally, we press equals, and we obtain a result of 0.572. We keep changing the value of a to obtain the different values of K sub z. We put those values in our tabulation. Next, we solve for Q sub z given by 0.613 multiplied by K sub z, K sub zt, K sub d, and V squared. We enter this formula into the calculator, noting that the only variable that changes is K sub z. To make this efficient, we assign K sub z to the calculator variable a. Then, we press the calc button and substitute the value of a with each K sub z from the table, one at a time. So Qz is as follows. Note that the last Qz, at level 10.35 meters, is also known as the QH or pressure at the mean roof height. This will be the Qz value for all of the other walls and roof. Okay, so we complete the column of Qz. Next, we add another column for C sub P. Into this column, we enter all of the C sub P values that we have previously calculated. The last two columns are a bit more involved. Here, we calculate the pressures while accounting for the internal pressure coefficient. The first column corresponds to the negative internal pressure, and the second to the positive internal pressure. On the calculator, we will use the colon function so that both the positive and negative cases are solved at the same time. You can certainly do this manually, but in my opinion, it is both safer and faster to set it up so that Q sub z and C sub p are entered only once for both calculations. For this, we replace Q sub z with calculator variable a and C sub p with calculator variable b, since those are the values that change. All other factors remain constant. We then press calc and provide the value of a, which is Q sub z, and the value of b, which is C sub p. Pressing equals will give us the pressure for the negative internal pressure case. Pressing equals again will give us the pressure for the positive internal pressure. We put those pressure values in the table. We will now repeat the same process for all the remaining levels and wall types. Following this procedure step by step will allow us to complete the table, just as shown here. The proper interpretation of these results is that we must apply both the negative and positive internal pressures, but in separate analyses, and then take the most adverse structural response. For hand calculations, this means we first use the negative internal pressure, perform the analysis and design of the structure, then repeat the process with the positive internal pressure. We then compare the two results and adopt the safer option. This approach is obviously more tedious, but it is fully aligned with the intent of the provision. With software, however, this process can be handled easily. Shown here is how the corresponding loads are applied to the structure, with the windward, leeward, and roof panels indicated. In the same way, here we see how the loads are applied on the sidewall panels. Finally, depending on how conservative we want to be, or on the time constraints we are working under, one practical approach, especially when relying on hand calculations without software, is to simply adopt the pressures with the higher values, whether they come from the positive or the negative case. I guess that is it. This concludes our lecture. Thank you, and I'll see you on the next one.